Okay, so I am already recording here, and we have Katy from Carleton, and she will bring to us the improvements in measuring rotational broadening in M dwarf stellar spectra. So, thank you, Katy.
Thank you so much. Yeah, my name is Katie, and today I'm going to be talking to you about measuring rotational broadening in M-dwarf stellar spectra. This work was done with lots of students at Carleton College, including Ali Keene, who presented earlier today, Freya Olson, Adam Ickler, with tons of support from our research supervisor, Ryan Tarian, and in collaboration with the whole HPF team. What is HPF, you may well ask? HPF is the Habitable Zone Planet Finder spectrograph, and its goal is to look at nearby M-dwarf stars. M-dwarfs are really cool, old stars that make for really interesting targets, and with HPF's high signal noise, high resolution spectra, we can probe lots of really interesting facets of these stars. In our case, we looked at what's called V sin I, also known as projected rotational velocity, which sounds a lot more complicated than it is. It's just the component of a star's rotation that we as the observer can see. So why would we care to measure V sin I in the first place? So rotation and magnetic activity are intrinsically linked in stars. And with stars like the sun, we know that relationship really well. With M-dwarfs, we can't say the same thing. We really don't know how activity works at all. So the more we can learn about rotation, the more we can start to kind of untangle the mysteries of magnetic activity in these late type stars. So how do we go about doing that? It relies on this concept called Doppler line broadening. And this happens when you have a star that's spinning and the side that's coming towards you, the light it's emitting gets compressed, so it gets bluer. The opposite happens on the other side of the star. The side that's moving away from you, the light it's emitting gets stretched out, so it gets redder. Then if we look at individual features in the star spectrum, the blue part of each feature gets even bluer, and the red part of each feature gets even redder. So you end up with broader lines overall. And the faster the star is spinning, the more pronounced this effect is. So we can directly link the V sin I with the broadness of these spectral features. So if we can find a way to analyze the width of these features, we can figure out how fast the star was spinning in the first place. To do this, we first need a thing called masks. And masks are just square functions where the non-zero part of the function matches up with the spectral features. So denoted in blue on this spectrum to the right here. And once we have the masks, we do something a little complicated with them. It's called the cross correlation function method. And there's a lot on this slide, so we'll step through it piece by piece. To the left here, we have 3 copies of the same simplified example spectrum. It just has 3 identical spectral features. And on top, we see the mask in green. You may notice that each mask is shifted by a different amount. And that shift is determined by this velocity value listed on the right here. We have v equals negative 100 kilometers per second, negative 50, 0. So that's not the V sin I. That's what's called the radial velocity. And if that term isn't familiar to you, not a problem. You can ask me about it later, but really the only thing you need to know about it is that it's what determines how much we're shifting the mask. So we have the mask laid over the stellar spectrum, and we want to multiply each point on the mask with each point on the spectrum. So in the first case, when the mask is shifted by a lot, so that the mask features don't really line up at all with the spectral features, if you multiply those pale green dots together and then add all of those combined points up, you're going to get a high value because you're multiplying the peak of the mask with essentially the continuum of the spectrum. If we do the same thing with the mask shifted by, say, negative 50 kilometers per second, you're multiplying the peak of the mask with a point maybe halfway down the spectral feature. So multiply those points together, add them up, and we get a value lower than we got with the first shift. Then in the third case, where the mask isn't shifted at all, so it's matching up kind of perfectly with the spectral features, if we do the same process, multiply the points, add them together, you're going to get an even lower value. So if we do this for a wide range of radial velocity values, a wide range of shifts, you're going to get a nice smooth curve like we see on the right here. And that's what's called the cross correlation function. Now, if we were to have a wider spectral feature, you would have to shift the mask by a higher velocity, in order for the mask feature to not line up at all with the spectral feature. So a wider range of radial velocities would have your mask kind of partly match up with the spectral feature, which means that you're going to get the broadness of the lines kind of encoded in the width of your CCF function, which means that the width of your CCF tells you about the V sin I of the star originally. So in order to apply this function to an actual star that we want to measure the V sin I of, we need to use something called a calibration spectrum. And that's a spectrum from a star we know isn't spinning very fast. We know it has a V sin I of approximately 0. And what we do is we artificially broaden that spectrum. We feed it a range of V sin I values, which broaden the spectral features. And then from that, we can measure the corresponding CCF function or cross correlation function and its width. And from that, we create what's called a calibration curve. So we just plot the input V sin I's and then the output widths from those broadened spectra. The use of a calibration curve will become apparent in a minute. But I think we can agree, even now, without knowing what it's for, that in order to have a good calibration curve, we probably want a good calibration spectrum. What do I mean by good? So when we first started out doing this, we used a single spectrum from a star called GJ699. It's a slow rotating M dwarf that we could say had a V sin I of approximately 0. Each gray line on this plot is one GJ699 spectrum. And as you can see, there's a ton of variation from spectrum to spectrum. This is due to noise, due to atmospheric interference, lots of different factors. So we combined all of these spectrum, essentially taking the average to create that red line, which definitely more accurately captures the actual shape of this stellar spectrum. So hopefully we've improved that calibration spectrum, but that's not all we need to create that calibration curve I showed you, right? We still need a mask. So we took a mask that was given to us by an HPF collaborator, and we went feature by feature through the mask, removing them one by one and seeing how removing a particular feature affected the output output CCFs we got. So in this case, before we remove a feature, we have kind of this odd shoulder feature on the left here, kind of an odd cliff behavior. As soon as we remove a single feature, our CCF looks much nicer. It makes it much easier for us to measure the width of this CCF without that cliff feature. So we did this with every single feature in the mask, and combined with the calibration spectrum, now hopefully we have a nice calibration curve. We can artificially broaden the calibration spectrum, use the mask to create multiple resulting CCFs, measure the widths, and create that V sin I versus width plot. But we're missing a whole half of this process. We're missing the part we really care about, which is taking a target spectrum from a star we don't know the V sin I of, and using the mask that we improved to actually create a target CCF, measure the width of that, and then compare it to the calibration curve and see what input V sin I it corresponds to. Because then that V sin I is our output. That's the V sin I of the star we want to find. So did we improve this method? By changing the calibration spectrum and the mask, did we make improvements? It turns out we did. So on the left here, we have a time series of V sin I over time. And the different colors represent different parts of the spectrum, different groups of wavelengths. And the fact that all the colors are jumbled together is a really good sign, because that tells us that different parts of the spectrum are reporting pretty much the same V sin I value over time. If we look to the right to these histograms, the top one is before we made any changes, and the bottom one is after we improved these parts of the process. And so the x-axis is the same. So even just looking at the shape of the histogram, we can say that precision has improved, and the standard deviation supports that. And when I say precision, I mean our ability to make the same measurement over and over again and get roughly the same value. You may also notice that the mean has changed as well, which suggests that we should probably make some sort of comment about the accuracy of these measurements. Unfortunately, we really can't comment on accuracy because there aren't consistent literature values for V sin I. It turns out this is a really hard measurement to make, and so there aren't really a reliable set of values that we can compare ours to. But just looking at precision, it's clear that that's improved, which is a really gratifying thing to see. Unfortunately, this picture is complicated when we look at a particularly magnetically active star, for example, BB10. So unlike the previous slide, there's a clear pattern to the colors here, which tells us that different parts of the spectrum are reporting very different V sin I values and consistently doing so over time. And this is pretty much exactly what we'd expect if we think that magnetic effects are contributing to the line broadening. We know that magnetic broadening happens to kind of different degrees and at different wavelengths. So the fact that we're seeing this very clear difference between different parts of the spectrum is expected, though still frustrating, because this means that we're no longer just measuring B sin I. We have this kind of systematic effect that is creeping into our measurement. That said, if we look at the histograms, precision has still increased. And in fact, because precision has increased is really the only reason we're seeing this pattern at all. The increase in the precision of our measurements has allowed this pattern to kind of emerge from the data and has alerted us to this issue. So as much as it's a complicating factor, it's a testament to kind of the improvements in our method. Going forward, this is definitely the thing we're focusing on at the moment. We've experimented with making masks out of just features that aren't affected by magnetic activity. Turns out that's a difficult thing to do because most features are affected by magnetic activity. But the fact that we can now make masks very quickly and test them out and kind of fine-tune things very efficiently, again, speaks to our increased familiarity with this process. And so makes everything we're doing going forward a lot easier. We're also looking at what's called telluric contamination, which is just atmospheric interference that kind of makes large chunks of the spectrum essentially unusable to us. And so working to kind of reclaim some of those wavelengths is something we're very interested in looking into in the future. And finally, the accuracy question, as new literature values come in, we will continue to compare them to the values we're getting and see how we match up against other people making similar measurements. So thank you so much for listening to my talk. If you have any questions, I would be happy to answer them.
Thank you, Katy. Any question? Anyone? Okay, I have a question here about when you did this work. Was during the summer or also or only during the semester, or how long it took you to do this, complete this work?
It's been a while. We worked on it both during the semester and during the summer. We've kind of hopped around to different projects involving HPF data. And so I think B sin I was kind of a spring, summer, fall sort of situation, if I'm remembering correctly.
Okay.
Can I ask how you measure the width? It seems like the width changes depending where you are.
Definitely. So that's, yes, that's a great question. So that's also, okay. That's why the CCF method is so helpful, because different parts of the spectrum definitely are going to have different line widths. And so by having this way to kind of incorporate all of them, you end up with kind of a nice conglomerated measurement. And it also reduces the noise and stuff. And so, yeah, and that's also one of the reasons why making masks with only a couple features, if we're trying to play with magnetically insensitive masks, is so tricky, because with fewer features, you don't get that same kind of canceling effect when you have kind of all of these features combined. Does that make sense?
I think you answered a more complicated question. Like,
Okay.
if I look at this picture you have here, if you measure the width at the top and the width at the bottom is 0 and the width at the top. And so, like, how do you know where to actually measure the width?
Standard full width half max. We just,
Okay.
yeah. Sorry about that.
No, your first answer was actually very nice. Maybe I should have asked the better question.
Any other question? Oh, so thank you, Kate, again. And I'm going to stop